Okay, let's look at question 3 now. In this, we had a couple of statements part of 3 nested loops, and we wanted to classify different variables into groups of whether they were read-only, read-write conflicting, non-conflicting, and whether they can be privatized or should be kept shared. And if they are shared and there is a conflict, how do we solve that? So let's start off with the easy ones. Let's identify the read-only variables. So in this for loop, the variables that are not touched as a part of, that is, that are not written as a part of for loop, as the for unrolls from I is equal to 1 to n, j is equal to 1 to n, k is equal to 1 to n, is the variable n. N is read-only all the time, right? And the variable x here, like this x here is read-only, and the n's are read-only, right? So n and x are read-only. Now let's look at the loop variables themselves, I, j, and k. So as we want to parallelize for I, each thread, when it goes from say 1, 2, 3, 4, it's taking the value of I is equal to 1, I is equal to 2, and so on, right? So I's value itself is conflicting, and each of the thread will also write j from 1 to n and k 1 to n. And similarly, the thread 2 will attempt at writing the j 1 to n and k 1 to n. And so when we are trying to parallelize for I, each variable I, j, and k is going to conflict. It's a read-write conflict, but it's easily privatizable to fix this. So we privatize these variables. Then when we try to do it for say j, so now I is equal to 1, for instance, and then each thread, as it moves from 1, 2, 3, 4, j is taking the value of 1, 2, 3, 4. So j is conflicting, and similarly k for each thread is going to go from 1 to n here. So the j and k will be read-write conflicting, but I moves to read-only. Similarly, when we do it for k, I and j will be read-only and k will be read-write conflicting. And in each cases, the loop variables are easily privatizable, right? So for ijk will be privatizable. For jk will be privatizable, and I will be shared and read-only. And for k, j and I are read-only and shared, and k is privatizable. Now let's come to the tougher ones, the loop variables. C, A, B, D, right? So let's look at C. C is here ijk, ijk, ijk. So as we unroll for the for loop from I is equal to 1 to n, j is equal to 1 to n, k is equal to 1 to n, in each loop, we are touching C, I, j, k. So this is loop independent. So irrespective of which loop we are parallelizing, C is going to remain read-write non-conflicting, right? So C was easy. Let's look at B now, which is B I minus 1 jk, B I plus 1 jk, B I jk. Just by looking at these loops, you can see that when we unroll each I, j, and k and assume values, like say for I is equal to 1, j is equal to 1. Actually, let's take I is equal to 2, j is equal to 1. Now k is going to go from 1 to n. B is going to go from 1, 1, 1, 1 is being read. 2, 1, 1 is also read, and 3, 1, 1 is written. As k goes from 1 to n, so this ones here are going to change, right? The I and j are going to remain constant. So k 1, 1, 1, k will be 2. So it will be 1, 1, 2, 2, 1, 2, 3, 1, 2, so on, right? So B doesn't necessarily conflict on k. So as you parallelize k, I and j remain constant and k's are varying, but there is no dependency across the loop for B on k. So it is easily privatizable, easily read-write non-conflicting when you are doing a parallelization for k and for j. But when you're doing it for I, because of the dependency of I minus 1, I plus 1 here, each thread is going to touch something that is going to be required by other threads as well. So B is going to be read-write conflicting for I. So now B is also done. Let's look at A. For A, we are touching this guy here and this guy here, right? So that is A, K, J, I, and A, K minus 1, J, and I. Even though the axis pattern is slightly different, and here we are trying to see it differently, if you try to visualize a 3D cube of these matrix elements, let's say it goes this way, and some entities within inside the cube. So say I is going this way, J is going this way, and K is going this way. So as I'm parallelizing for I, let me reorient this. Yeah, this is for A, right? So A, K, J, I, and K minus 1, J, I. And so we have this cube where I is going downwards, J is increasing from left to right, and K is going like that. So if we are parallelizing for the loop for I, so each thread is going to take I's value of 1, 2, 3, and so on. So what that means is I's values are parallelized. So each plane, like this KJ plane, like that, there would be a plane here. So these individual planes are going to be parallelized for I. And within that, each thread is actually, as the value of K and J increase, they are actually going to go like this. I think so the K's value increases first like that, and then like that, and like that, and like that, right? So when you are parallelizing for the plane, for the loop I, each planes are disjoint, and none of the loops are crossing the planes. So it's easily parallelizable for I. Similarly for J, it would be, so the I is fixed and now the J is also fixed. So it's just the K like that. Each thread is going to execute these. Then the next IJ, the threads are going to go like that, right? So A has again no conflict for I or for J, but it will start having a conflict for K with the K minus 1. If you substitute the values for each I, J, and K, you can easily come up with a conflict for K. Now, when we look at D, D is slightly tricky. So D is here, D is touched here, here, and here. So the values for D that are being touched are D, K, K, I is being written to, and D, I, J minus 1, and K is read above this statement twice. But it's thankfully the same two variables, I, J minus 1K, I, J minus 1K. So let's look at D as well in the same manner, right? Let's visualize a 3D cube. So if we are trying to parallelize for I, each thread is going to get a value of 1, 2, 3, 4 separately, and J and K are going to increase, right? So if we try to see that way, say again same, I is this way, J is this way, K is this way. For the read that is happening, I, J minus 1, and K, each of the plane is what we are trying to parallelize when we parallelize for I, because we are parallelizing at this level, right? Like I, for each value of I, that means this, this. So each threads are acting like that on an individual plane. So even though we are reading from different planes, the right actually, because of the axis pattern, is going to come across like this, right? Because for K11, K22, for a given I, it's just gonna go something like that. It's going to go across the planes on this surface. So when we are parallelizing across planes of this guy, we are actually accessing dkk like this on these surfaces, the blue ones. So there is a conflict. So for I, there is a conflict. If you similarly see, there will be a conflict for J as well. The conflict won't be there for K, because when we are parallelizing for K, each thread is going to do this individual element reading, and then writing will be for these individual elements. So the axis patterns are going to be parallelized much more, but it's not completely true. Like there will be one entity which will actually end up in each axis pattern conflicting, but overall the K moves like this, then it will move to the next J, and so on and so forth. But the right, so this is for the reading, and then writing is gonna go like this across planes like that. So there will be disjoint axis patterns, but there will be some corner cases when they actually do meet. So if you put D as read-write non-conflicting or read-write conflicting, I've accepted both the answers for the K loop. But for most of the pattern, you can see actually that they can remain read-write non-conflicting. Now, because these operations that are happening on each one of them are each matrix has like a weird sort of dependency when you are parallelizing for I, for J, or for K, and then they are not simply being additive on themselves, right? Like for instance, D, I, J, K is not some amount of Aijk plus Bijk, and then like you can't reduce them easily. So it's very tough to use reduction for any of these matrix elements right now. So whenever you are parallelizing and then there was a read-write conflict among them, the only way is to use synchronization here. Like either you do across for a simple case of say B, when you were parallelizing for I, you can do across, but like you have to post and wait, like you have to post the right element and wait for the right element and use such sort of synchronizations. Okay, so that was the question 3 for homework 1.